news articles that I thought were interesting. Of course, the big news is the Trump ban. Trump was banned on Facebook after the January 6th insurrection, and Facebook's board just said they should continue that for another 6 months while they try to write better rules. So the Republicans are really angry, threatening to break up Facebook, saying this is a terrible thing and you could be next and they should have no right to ban anybody and stuff. So as you'd expect, although the threats to break up Facebook are probably not empty, the right and the left are both very, very angry at Facebook. This is the first time I believe I've ever heard of Facebook doing the right thing. But of course, it puts Mark Zuckerberg right where he didn't want to be. Mark Zuckerberg has been begging for someone else to please make this decision. He said, why doesn't Congress pass some rules? Why doesn't somebody just tell me who to ban, and then it won't be my fault? And then he tried to form this separate independent body, hoping they would decide, and they just said, no, you make up some rules. So this means he's going to have to make the decision, and of course, to make money, he's screwed. He has to either piss off the right or the left by making this decision, and he was hoping to somehow avoid making that decision, just like I'm sure most American companies would like to somehow court both the right and the left in our rapidly dividing country, just like in the time of the Civil War, when the whole nation is splitting into two halves, and you can't possibly please both halves anymore. That's pretty much where we are, and doesn't look like it's going to change anytime soon. So Trump made his new social network yesterday, which is just a blog. And he has different rules for both parties. Well, that's what the Republicans think. The Republicans think he has different rules for each party. And Facebook tries to say they have the same rules for each party, but this independent board said, you don't seem to really have any rules. What you do seems to be arbitrary and not make any sense. You really have to write some rules. And so they're going to have to try to write some rules. Certainly all the other people complaining about Facebook bans have said they have no rules. Like if somebody threatens to kill you and dumps out your name and phone number and sends people to your house and you're not famous and you complain, they won't do anything. Neither will Twitter. They couldn't care less. You can break all the rules all day unless you are too important, and then they'll make some random decision about whether to ban you or not. And, so the independent board is quite correct. Facebook doesn't have any rules and they don't have any clarity in when they enforce them. And that's not easy, but they kind of have to do that. If you make this platform, you have the obligation to police it somehow. So they've been told they have 6 months to come up with some rules. We'll see what happens. I don't know how you'd write those rules in the current political climate where it please both sides, but at least you could write them down. The idea is there ought to be some rules, and then somebody like Donald Trump ought to be able to read the rules and obey the rules and get back on. That would seem logical. So we'll see what happens. Anyway, so Trump has made up his own blog, and he has put some Twitter accounts to try to retweet things onto Twitter from his blog, and they've been catching them and taking them down. So they found a series of them here. They're just from the desk of Donald Trump, desk of DJT. He's trying to evade the Twitter ban, which is not working too well so far. And this is something I'll be talking a lot more about next semester. Like I say, I'm going to be talking about cryptocurrency, and that means it will just be a litany of the crime of the day. And here's the crime of the day, Tether. Tether is just added to Coinbase as if it's a real currency. Tether is a completely fake currency that pretends to be tied to a dollar, that pretends to be backed by a reserve of dollars, which is just a lie. And they print more Tether as fast as they want to, just to prop up the price of Bitcoin. And they just printed 2 billion in Tether earlier yesterday. So this is why the cryptocurrency price goes up. They pump it up with Tether. And it's now being taken as a serious currency like Dogecoin, which also is complete nonsense and should never have been taken seriously, but now it's also going to be treated like real money. This is what happens in these times of boom after a pandemic. It happened in the 20s too, the 1920s. Anyway, here's one of the auditors who claims to be an experienced auditor of many audits, explaining what's going on with the bizarre tests they're doing in Arizona. There is a conspiracy theory that a whole bunch of fraudulent ballots were shipped in from China, and because they come from China, the paper contains bamboo, and you can then run them through some kind of X-ray scanner or something and find bamboo fibers in the paper, and that will prove that they're fake, imported from China. So that's the kind of stuff they're testing for. Of course, this is all nonsense. I highly doubt that paper from China has bamboo in it. Not that I really know. I highly doubt that a bunch of fake ballots were shipped in from China. As a matter of fact, I don't know where the official ballots are printed. Pretty much everything does come from China. It would be kind of funny if the official ballots are really printed on paper that came in from China. That wouldn't surprise me too much. Anyway, all right. So I don't think I need to talk about these other news reports. We'll talk about them in other classes. So here we are today. This is 126. No, it's 128. All right. I'm trying to remember what day it is with increasing difficulty. All right. So we're down to attacking iOS applications. That's the plan. And we'll have the second half of this next week, and that's the end of the class. And like I say, all I got is a lecture. I don't have labs for these things because all my iOS labs are totally failing again. And I'm not going to be able to fix that this semester. Maybe next semester. They keep on upping the security of iOS faster than I can keep up with it. Well, next semester, fewer teachers, that is perhaps not true. The latest thing I heard today is maybe they're just going to cut our pay by 25%, and then they'll only fire the part-timers and they won't fire the full-timers. So nobody really knows what's happening next semester yet. But supposedly they've told me what classes they expect me to teach, and it's the ones I asked for pretty much. So we'll see. Anyway, so we're going to talk about transport security, which is TLS, which you may well know about from other classes, and then insecure local storage, and then we'll talk a little bit about patching the apps with Hopper, which is one of the many tools you could do it with. And there's a few things to talk about in the next chapter too. So if you want to attack an iPhone, here are possible ways to attack it. One is from the network. If you can somehow feed data into an application that's malicious, or you can have physical access to the phone. You steal somebody's phone or impound it because you're the cops or something, and now you have perhaps some way to get at the data on the phone. And then there's the one we talked about with that Drozer tool on Android, where you have control of another app on the phone. So I managed to sneak some kind of malicious app on the phone which can attack the other apps, which is not easy to do, but it can be done sometimes. So the main thing here is TLS. This is your main defense. So if you send data over HTTP, this is never safe because the data is not encrypted and the server that originates the data is not authenticated in any way. So anybody can just modify that data on the way to your phone and you have no way to know that that's happened. They can read what you're doing, modify it, and they can read the responses and modify them. They can therefore inject script into the response, which will execute in your browser. So loading pages over HTTP basically gives anybody remote code execution on your browser if they can get in the middle, in between you and the server, which is not that difficult to do on a one-on-one attack. It is hard to do en masse or from a great distance, but if they can get in the same coffee house as you, they can do it pretty easily. So you can just examine the traffic and see if it's encrypted or not with Wireshark or BERT or any other tool that lets you examine the network traffic. And so let's talk about what errors are made that messes up TLS. There are 3 implementations of TLS stacks in the Apple iOS: the URL loading, Carbon framework, and the secure transport API. The main one is the URL loading system, and this is like Microsoft's Internet URL API. This is the high-level system that will just connect to a URL you feed in, and it's easy to use, and this is what they expect most apps to use. And it will then automatically take care of all the details below that level, and that is normally what a normal person would do. The Carbon framework gives you greater control over the network requests and uses this thing called CF network class, but there are parameters and you can possibly adjust them in such a way as to create insecure traffic. And the secure transport API is even lower. This is what's used to power those more high-level ones above it, and here you have the greatest control. This is, I think, close to what you call raw sockets in the world of Unix. So the point is, it is a complicated handshake to make a TLS connection. It's a 7-stage handshake, or even more if you consider the certificate authority. It has to make a request, open a TCP port, then negotiate a Cypher suite, then get a certificate and validate it. It's got quite a lot of steps to go. If you do TLS correctly, it is really very difficult for anybody to snoop on it or modify it. Nobody can do it except nation-state actors or really large hacker organizations that have access to trusted root certificates, which they're not supposed to have access to. So there's a trusted certificate authority. Hard-coded in all your browsers is a list of about 100 trusted certificate authorities, and you will only trust a certificate that has been purchased from one of those companies, that is signed by one of those companies. And that's the plan. If you accept a certificate that is unvalidated, not signed by one of those companies, or just self-signed, so it doesn't go to any root at all, then that would not be a proper TLS connection, and it could be man-in-the-middle, and therefore you should not accept those things, and you're not doing proper TLS if you do accept those weaker certificates. So in the NSURL connection class, you can allow these by customizing a method, authentication challenge. And in the Carbon framework, you can allow it by setting up something called an SSL settings dictionary, which has parameter adjustments, and you can turn validate certificate chain to false. And then it'll do just what it says. It will not test certificates. In the Secure Transport API, there's another one here. You can set an option called break on server auth, and that will disable the certificate validation. So again, that would allow a connection made with an unverified certificate to be accepted by the operating system as correct. However, the app might have certificate pinning, which is another layer of defense built into the app and not dependent on the operating system. And if that's true, then any of these other adjustments would not fool it. So here's the common certificate problems. Some people use self-signed certificates, expired, mismatched host names, expired root certificates, or a root certificate that's not on the trusted list. These are the kind of bad certificates that might be out there, and a proper app should not accept any of these things. So, you can route the traffic through the BERT Proxy. Here's what it looks like on Android, but you can do the same thing on iPhone. And then when you try to connect through the proxy, it will tell you your connection is not secure and give you an option to ignore that usually, but you are warned that you're not going to see it, that you are receiving an unvalidated certificate from BERT. Here was a flaw in 2014, which meant that all the certificates have been unvalidated for a long time. This happens a lot. A lot of apps don't validate certificates, and typically nobody ever notices. Users can still use them. The traffic is still encrypted. It's not obvious to everybody that there's a problem, and it often persists that way for years with nobody noticing or caring. And the entire iOS operating system had broken this. They'd broken it because of this. They wrote this. This was attempted to be a case statement. So if the error was like this, it would go to fail. If the error was like that, it would go to fail. And then because they had an extra line here, it would then, if this was not true, it would go to fail. So it would never make it down to this statement. It would always go to fail and return an error. But this meant if certain hashing values were just correct, it would exit and the error code would indicate success. So it would succeed even when the certificate was invalid. And it was this way for a long time without anybody noticing. Then it came out as the famous go-to-fail vulnerability. Apple pushed out a patch, and everybody complained and yelled at Apple for making this mistake. They made similar mistakes. There was a very similar mistake is what led to the checkbrain exploit we've been using to jailbreak iPhones. They changed malloc, and malloc returned the size of the, returned a code showing it had allocated size, but there were certain conditions under which the actual size of the data would be 8 bytes bigger than the allocated space and overrun. That was the heart of the checkbrain exploit, with a very simple little source code mistake. So that's the game here. Signature validation will never fail. So they patched that, of course, back in 2014, so nobody's probably using a machine. Yeah, Heartbleed was similar. Yeah, Heartbleed was a similar one to another one I just saw recently where you had a packet of data and then you had a size parameter of how much data was in there, and it did not verify that the data matched the size parameter. So you could send it a request with a small size parameter but a large amount of data, and it would then overflow. This is a concept we'll talk about tomorrow in the CISSP class, but you don't want to have two numbers that imply the same number, because that makes it possible they will contradict each other. Everything important should just be in one place. Otherwise, you have this kind of trouble. Anyway, so that's the game here. All right, so there are other possible errors if you're using the old one, but not if you're using the high-level one, because you can't quantify much. Anyway, then there's protocol versions. These allow a developer to modify the version of the protocol, and you can even modify it to the really old deprecated ones like SSL2 and SSL3, which shouldn't be used at all anywhere anymore. They've been considered unsafe for years. All right, and just keeping an eye to see if groceries appear here. So here's how you specify it in the Carbon framework to use various versions, and SSL is quite insecure. Here's ones that allow you to negotiate down to insecure versions. And the recommended one is this one, which tries to use TLS 1.2, which was the most recent version at the time they wrote your textbook. There presumably is one to set for 1.3 these days. It'll try to use 1.2 and negotiate down to 1.0, but no lower. And those are all pretty good. When you do the transaction, if you catch it in Wireshark, it does a SYNAC-ACK can open port 443, and then your browser sends a client hello to the server, and the client hello goes like this, saying, I am trying to talk TLS version 1.2, and here are the Cypher suites I have, like Galois counter mode and Cha-Cha and ECDHE, and we'll talk about all these in the cryptography class if you're not familiar with them. And a lot of these are pretty much all very good. ECDHE, Cha-Cha. These are good modern suites, but you have 17 possible encryption suites I can speak. And then the server will look, and then you'll negotiate one to use. That's what goes on. Your browser has a range of encryption methods it can use, and the server has a range of encryption methods it can use, and you try to negotiate the strongest of those two options. All right, so a developer can specify an insecure suite. You could tell it to force it to use an old one, like RSA with RC4 and MD5. All old RC4 and MD5 are now deprecated, not recommended anymore, and so this is an old suite that's not very good, and you could code something that forces it to use an old suite for your app. I don't know why you would, but in principle you could. All right, so as I say, if you want to install, as we've done plenty in Android, are the free certificates from EFF good? Yes, they are. They've greatly changed the world, but Let's Encrypt. The Let's Encrypt certificates are perfectly fine, and they can keep up with the load too, and a lot of people are now talking about changing your certificate very frequently, like every week or so, just automatically getting a new certificate to mitigate the consequences of a stolen certificate. So yeah, they're perfectly fine as far as anybody can tell. Anyway, so if you can put BERT in the middle by just setting the proxy settings, and then all the secure connections will fail unless you install the BERT certificate on the phone, which you can do on an iPhone, and then you're telling it to trust BERT, so it won't have any errors anymore, except for sites, apps with certificate pinning, which BERT can't fool. So if your app has certificate pinning, then it has some other test where it looks at something like the name of the certificate authority or something, and so you'd have to bypass that. Now, one way to bypass that would be to modify the app and reinstall it, but that is in fact very difficult to do on an iPhone because you can't get it in the store. Another way to do it is with Substrate tweaks, and these are what I really like to have in the hands-on projects, but they keep on breaking for me. The point of Cydia Substrate is you can change the function calls underneath the app, like the API. So the app stays compiled, but you change the operating system under it, sort of like a rootkit, to change what those API calls do. And it's pretty awesome and lets you put anything you want on the phone, and it has to be jailbroken and such. And there are various ways to do it, but they keep on changing with different versions of iOS, and I wasn't able to get them working very well last semester, so I took those projects out, and I haven't been able to get them working this semester either. But that's what Cydia Substrate does. All right, and then there's insecure storage, which I was finding for a while on iPhones, and I decided not even to report it to the companies because I'm not sure it's a real problem anymore because of iPhones extreme encryption of local storage. So you can store something on your phone, like your app may store a password or a credit card number or something on the phone. And so if somebody steals your phone while it's unlocked, before it goes to sleep, then they can get at your stuff. Or if they manage to bypass the Touch ID sensor and somehow log in with, like, I don't know, a copy of your fingerprint or something. Okay, good. All right, my stuff is not here yet. Or you exploit it somehow. If you're able to, if your phone is jailbroken, of course, then they might have default credentials like root and Alpine, or no passcode, or these other techniques. But might be a way I can actually authenticate into the phone and unlock the encrypted data, and then I'd be able to steal the local data. But for a normal iPhone that hasn't been jailbroken with a normal PIN, these are really very unlikely to happen. All right, so if your app stores plain text stuff or with custom encryption, or stored with the wrong data protection class, or perhaps stored by the iOS, these would be errors. And of all these, I thought these were extremely weak, except for this one. Storing it with the wrong data protection class is about the only one that I would regard as a reportable vulnerability. And the apps have been testing. And remember, there's the data protection API and all these different classes here. Like here's none class, where it's really not encrypted at all. And as long as the phone is running, you can read it. But anything sensitive should be over here, where you need the passcode key to get in. And then if the phone is locked, it can't get at any of that until you type in the passcode. That's the point of these things. So you should be over here for sensitive data. So that's the point. This one's uncertain. Complete until first authentication is also discouraged, because if the phone goes to sleep and you wake up, it's still there. Anyway, to find out what data protection classes you've got, you could back it up and then use this to examine the backup, and it will show you the data protection class of the data it manages to back up. You can go to the Keychain and run Keychain dump, and it will make a file that shows you the protection classes of things. These are ways to test it. All right, so if you want to test stored data that doesn't get backed up, then you could use Cydia Substrate. There used to be a tool called Snoop It, but it seems to be gone. You know, these tools that reach deeply into iOS don't last very long before the iOS updates make them stop working. All right, and if if a jailbreak an iPhone, you can pull an app off the phone the way we did with Android, and you can unpack it and then examine the source code. Well, you can examine the object code. That's all you get. That's the problem. You can use dump IPA to list the apps on the phone, and then you can pull. This will dump the app off the phone, and it comes down as an IPA file. So this is the actual app, like the APK file that you get off an Android phone, and you can unpack that and disassemble it with Hopper, and you will see assembly code. This is i86 assembly code on this case. Now, I don't think it should be ARM assembly code for an iPhone. This must be ARM assembly code. Doesn't look like it, though. Anyway, you've got assembly code that you have to read. You don't have source code like in Java or Smalley, but you can still see things here. Like here's the list of stored strings, and here's one that says this device is jailbroken. So this has jailbreak detection, and there's the string it would print out. And if you look for references to that string, you could probably find the code that does the jailbreak detection, and you might be able to figure out how to dodge it. And Hopper, like Ghidra, can decompile code. It can turn it back into pseudocode, which is sort of like C, which is somewhat readable. So here's the code that does that jailbroken. If some initiated with title security violation methods, and here's the arguments, it's still not very readable because you don't have the names of the variables or the names of the methods. That's what you get with decompiled code. It's not as good at all as Android Smalley code, not as easy to read, but it is easier than just reading the assembly code. All right, and I've got some Cahoots about that. And so that should be Chapter 3A. This one here. All right, looks like that's it. All right, so what scenario would use malware in the App Store? That's called interactive. You can do an interactive attack against the phones with the malware on them. This happens all the time in Android. It's only happened a few times for the iPhone. The iPhone App Store is really quite clean because the punishment for putting malware in the App Store is so dire. They kick you out and you can never come back, and you can never make any more money as a developer. That's enough to discourage it. All right, what's the most common implementation? Yeah, normally you'd use URL loading. It's the easiest and highest level. Why would you really want more granular control over the network packets? Unless you're doing something screwy, most people just want normal HTTPS or something. All right, you install the BERT certificate and you still cannot intercept network traffic. What would cause that? All right. Yeah, that's pinning. That means that even though the operating system is accepting the certificate, the app is not accepting the certificate. All right, so how do you get user data from a stolen, locked phone? Yeah, if you can bypass the touch sensor with something like a fake thumbprint, that might get in. Neither of those are going to get you in. All right. So let me record the winners. Okay.